All right, this is what I'm going to call my very brief and utterly oversimplified history of atomic structure. What I'll be giving you is just a very basic physical science level approach to the history of atomic structure. It is much more complicated than this. There are a lot more names involved in this, but it does cover the very basics of what you have to know for physical science in the end of course exam. The whole idea of atoms starts with a Greek philosopher named Democritus. He's the first person to suggest the existence of atoms, to suggest that matter is composed of tiny particles called atomos. Like a lot of things related to the nature of matter and the universe around us, it was ignored. There are more important things in life than worrying about what matter was made of. So for about 2,000 years, these ideas were pushed to the side and not thought about much. That was until John Dalton comes along. John Dalton takes a lot of these ideas from Democritus and from other scientists that came before him and proposes his atomic theory. There are 4 points to his atomic theory. First, all matter is composed of tiny particles called atoms. It was a bold, brave statement because not even John Dalton knew what atoms were. Atoms are not created or destroyed. In a chemical reaction, whenever a chemical change takes place, atoms are just rearranged. Atoms of an element are identical but different from every other element. And then, again, another bold statement because he didn't know what atoms were. But what he's saying is if you had a chunk of gold, an element, that every atom in that chunk of gold would be identical. They'd be different than the atoms of carbon. They'd be different than the atoms of oxygen. What he's basically saying here is it's the atoms that make elements unique. That elements are composed of atoms, ideas that we've already covered. And he said atoms always combine in whole number ratios. When they combine to form a compound like water, it's a 2-to-1 ratio of hydrogen to oxygen. It's always whole numbers. There's never half an atom in a compound. So basically telling us that these atoms are the building blocks of all other matter. Again, Dalton didn't know what atoms were. It wasn't until J.J. Thomson comes along much later on that we start to put the pieces of the puzzle together. Thomson discovers what we now call the electron. He did it using what are called cathode ray tubes or CRTs. Basically a vacuum tube with 2 electrodes in it, one positive, one negative. When they were hooked up to a power supply, a beam would shoot across the tube from one electrode to the other. He did experiments with this beam. One of the experiments he did was to subject it to magnetic fields to see how the beam interacted with magnetic fields, whether it would be attracted to or repelled by magnetic fields. And what he found in these experiments was that this beam was charged. It had an electrical charge to it, specifically a negative electrical charge. Then he needed to see if this beam was energy or if this beam was matter. And as the story goes, he put things inside the tube to see if the beam would interact with those objects. And it did, telling him that the beam was made of matter, so some negatively charged matter. He called it corpuscles. He called these particles that make up this beam corpuscles. We later changed the name to electrons. He took these ideas and created the first model of the atom, the first description of what an atom might look like. It was called the plum pudding model. Plum pudding was a popular dessert item of the day. We might better off think of it as the chocolate chip cookie model. In his model, the atom was this massless sphere of positive charge. Think of it as the cookie dough. The electrons were just scattered randomly through that positive charge. You can think of the electrons as the chocolate chips. It was his best shot at what an atom might look like. He didn't have the whole picture. We now know that this is very wrong. But it is the first model of the atom. Ernest Rutherford is next. Ernest Rutherford changes the idea of the atom dramatically with his discoveries. He first discovers a proton, the positively charged particle, and he discovers that these protons are in a densely packed cluster called the nucleus of the atom. His model is called the planetary model. You have a nucleus in the middle. The nucleus is where all the protons are. The protons are jammed together in that nucleus. The electrons orbit the nucleus in these neat circular paths, very much like the planets orbit the sun. He says that this atom is mostly empty space. That the nucleus in the middle, very, very tiny. The electrons orbiting it, again, very, very tiny. Most of what the atom is absolutely nothing at all. Totally empty space. He discovers all this. He comes to this conclusion doing what's called the gold foil experiment. What he did is took a very thin sheet of gold foil and he shot radioactive particles at it. He noticed a couple things. He noticed that most of the particles just went straight through the gold foil. This is where the idea of atoms being mostly empty space comes from. Since most of the particles went straight through the foil, most of the foil must be nothing at all. It must be empty space. He noticed that some of the particles were deflected. Their paths were changed. It came in one direction and it came out of the gold foil another. He determined that this deflection was caused by electrical repulsion. These particles that were being shot were positively charged, and they were being repelled by something that was positively charged. That's where these protons come from. He noticed further that even a smaller number were hitting the gold foil and bouncing off, coming right back at him. He determined that in order for this to happen, these particles must be hitting something that was relatively large, relatively massive compared to the radioactive particles. This is where the idea of the nucleus comes from. These particles, he presumed, were hitting the nucleus of the atom, where all the protons were clumped together. Because all the protons were there, it had a relatively large mass, causing the radioactive particles to bounce off. His model is called the planetary model, and there's a couple of problems with the planetary model that he came up with. First of all, there was a big mass problem. When they were working with atomic masses in Rutherford's model, they found that the masses and the number of protons didn't add up. There were fewer protons than what the mass suggested there should be. There's something in the nucleus other than the proton. And it's James Chadwick that discovers what that something is. He discovers the neutrons. So he takes the planetary model and he tweaks it a little bit. We have a nucleus in the middle still. But instead of that nucleus being made of nothing but protons, he adds the neutrons to it. The electrons still orbit in nice circular paths. Does a couple of things for us. One, it fixes the mass issue. Now the masses are what they should be. They're predictable, they're what we expect now. And it also takes care of repulsion problems in the nucleus. Because the protons are all positive, they should be repelling each other, they shouldn't want to be in the nucleus. These neutrons produce what are called strong nuclear forces that hold that nucleus together, keep it from falling apart. So it fixes a lot of the problems that Rutherford had in the planetary model. And this model is accepted for a relatively long period of time. In fact, is the standard model that's still taught in elementary schools. It still has problems, though. And perhaps the biggest problem that it had dealt with the orbiting of the electrons. Bodies that typically orbit other bodies will eventually see their orbits degrade, decay, until they crash into that other object. Electrons don't do that. Niels Bohr comes along and fixes that issue. Instead of having orbits in his model, the Bohr model has what are called energy levels. Instead of the electrons orbiting the nucleus in these nice, neat circular paths, the electrons exist in what are called energy levels. And you can see in the model here, this one shows 3 energy levels around our nucleus. This is the atom of chlorine. It shows 3 energy levels around the nucleus. The electrons that are within a level have similar energy. So these 2 electrons in the first level, they have very similar energy. We have 2, 4, 6, 8 electrons in the second level. They have very similar energy. These 2, 4, 6, 7 electrons in that third level, again, they have similar energy. The ones closest to the nucleus have the lowest energy. The ones furthest from the nucleus have the highest energy. The electrons move randomly inside these energy levels, not in nice, neat circular paths. More like moths flying around a light bulb. They go just wherever, whenever. He suggests that the electrons can move from one level to another. That if you heat this up, or if you pass a strong electrical current through it, that you can make these electrons jump from the first level to the second level, or the second level to the third level. That if you take that heat away or you take that electric current away, they will drop back down to the lower levels again. They can move back and forth between these. They're not stuck at any one energy level. He came up with this idea looking at what are called line spectra. When an element is excited with electrical current, like a noble gas like helium, it'll glow. And looking at the specific wavelengths of light it produced, it suggested that it had these energy levels in it, and that each wavelength corresponded to the electrons moving first up into a different energy level, then falling down into a lower one again. Again, based on that evidence, he came up with these ideas of levels instead of orbits. Now, we stop there. The modern model does not. When you take chemistry classes, you'll learn about things called orbitals, how these energy levels are divided up into orbitals, and how it's not a confined space at all, how it's based more on probability than it is on actual location. But again, this is where we stop in physical science. As usual, if you have any questions or concerns, please feel free to post them all along, or see me sometime before or after class.